then we also briefly discussed perturbations set up in the initial conditions due to inflation. And these perturbations, we want to know what happens to them as time evolves. Okay, so starting from some very early form. So broadly speaking, we want to know how the universe goes from like this, which is a snapshot of the universe at 380,000 years after that, to looking like this, which is a snapshot basically today. So this image is from the Sloan Digital Sky Survey, and here now the density, the color indicates the density of points. So here you can very nicely see this large-scale structure that has emerged. You have these filamentary network of filaments, right? Straight lines like this, here, and then they intersect at these very high-density places. A lot of galaxies, and then there are regions, as I was saying earlier, also. There are very, very few galaxies. So there are voids which are surrounded by these filaments. We don't know how this emerges. So today we have a reasonably good understanding of why such a structure should emerge. So what I'm showing you here is a numerical simulation, okay, of structure formation. So what you can see is the time is running along here. So time is being measured in redshift now. So high redshift means early times, and now we are going towards redshift smaller and smaller. Redshift 0 is current time. Okay, so this is the way the clock is running. And I'm showing you one slice of this simulation box. It moves around. So now it's gone back to high redshift and it's coming down to low redshift. So you can see that at early times, it looks very smooth. And then as time progresses, you can see these dense regions forming. So the color here is the over density. So it is 1 plus delta. The reason I write 1 plus delta is I'm defining, so at any given point, if my density of mass is rho, x and t, I can divide it by the mean density of the universe at that time, and I define this to be the dimensionless quantity 1 plus delta of x and t. Okay, so this 1 plus delta is just a dimensionless forward and logarithmic scale. So wherever you see red, later on you see here there will be a red patch forming. So that place is more than 100 times the density of the mean density of the universe. And then here, when you deep blue, for example, here, you're going down to densities that are less than 1/10 of the mean density of the universe. So very overdense regions, very underdense regions. The density from here to here, in the initial conditions, you see everything is around this cyan to light blue. So everything is close to the mean density. But as time progresses, the density contrast between this place and let's say this place is what? 3 orders of magnitude, okay, at least. And then this depends on the resolution of the simulation, etc., how well you can resolve these structures. But it is very clear that whatever the simulation is doing, it's a black box for you just now. I've not told you what goes into it. But whatever it is doing, it is creating a structure that looks not very different from the structure of those galaxies that you were seeing before. Right? So you also again have these filamentary patterns, and you can see these high density regions are typically sitting at the intersections of filaments. Here there are many such filaments that come in, right? And the individual filaments themselves have high density regions embedded inside them, and so on. Whereas here there are thinner filaments which don't have these high density regions that you can resolve. So the simulation is doing something which seems to be realistic. Okay, so this is like the final answer. Okay, after everything we have figured out, this is what one has to do. So this lecture is going to be about building up some of the physical arguments that go into arriving at this picture. Okay. So in order to understand what is happening in structure formation, one has to first understand what happens with length scales in the universe. Somebody asked a question about co-moving versus physical length scales, and then in terms of the wavelength of the perturbations, the physical wavelength of the perturbation will change as a function of time, what happens to the Hubble radius. These are extremely relevant questions, and this is what we will discuss to begin. Okay, and I'll spend some time on this, 5 to 10 minutes on this, because it is very important to understand this. Without understanding this, what happens to the late time structure formation is very difficult to figure out. But if you understand this, you can always go back to this set of arguments and understand things based on them. Okay, so we will spend some time on this. After that, I will talk about what is called the linear regime of perturbations, where you say that in the initial conditions, the density contrasts were very close to 1. Okay, so the density contrast is usually denoted by this delta. So that is very close to 0. So the over density 1 plus delta is very close to 1. And only at late times this over density becomes very large, either very large of the order of 100 or very small of the order of 0.1. Okay, so at least at early times, where the density contrast is not very large, or when you can think of the universe as it looked when the CMB was released. Here the fluctuations are 1 part in 10 to the 5, right? So 1 part in 10 to the 5 means this delta is of the order of plus or minus 10 to the 5, 10 to the minus 5, correct? So 10 to the minus 5 is a very, very small number compared to 1. So in any equations which involve delta, if I see powers of delta appearing, for example, if I see a delta squared appearing, then I am 100% sure that this delta squared is very negligible compared to delta itself. Because if delta is of the order of 10 to the minus 5, then delta squared will be of the order of 10 to the minus 10. Okay, so I can neglect places in the equations where powers of delta appear, more than 1 power of delta. And similarly for other quantities which may be interesting. For example, if I want to think of the mass of the density of this fluid, it's not just the density of the fluid that will be relevant. When you do fluid dynamics, you have to at least discuss the velocity of the fluid also. And then maybe you have to discuss the pressure of the fluid also. And there is a gravitational potential which is affecting everything. So all of these things are fields which are varying across space and they are evolving in time. And what we are saying is that these fields are all describable as being small perturbations around whatever the smooth expanding universe was doing, which we studied using Friedmann's equations. Okay, so Friedmann's equations have to be modified, and the evolution of these perturbed quantities will then become whatever equations you have to solve. So this is what we want to do, and in the linear regime, you will say that I will throw away all powers of delta, velocity when they multiply each other. I'll only keep terms in the equation which have 1 power of delta, 1 power of velocity, 1 power of potential, and so on. Okay, so that is the linear regime, and it is very useful to study this regime because you can solve things analytically. Because you get systems of ordinary differential equations which are very easy to solve. At later times, when the universe starts looking like this, it's clear that this approach will not be valid anymore. Because when 1 plus delta is of the order of 100, what is the order of magnitude of delta itself? Louder, please. Also of the order of 100, right? It's an order of magnitude estimate. Exactly. So if delta is of the order of 100, then I cannot say that delta squared is negligible compared to delta. In fact, when delta is of the order of 1 also, I cannot say that delta squared is negligible compared to delta. So, although your linear regime calculations are easy, they are not relevant when nonlinearities emerge. Okay, so the equations, as you will see, are nonlinear. So, when the density contrast becomes large, you have to account for these nonlinearities. But the equations then become very complicated. You cannot have analytical solutions in general. And the general situation is when your initial conditions look like this. They are a Gaussian random field. Okay, one realization of a Gaussian random field. So from place to place, you cannot predict exactly what the density structure is going to be because it is the realization of a random field, right? So you have to come up with other techniques to approach these equations. The most accurate technique we know of today is this numerical technique called the n-body approach, okay, and variations of this. So that is why I'm showing you this result right at the beginning. This is the most accurate answer that you can come up with today. But it is still useful to develop less accurate, more approximate techniques to approach these equations because they allow you to analytically solve some of these equations and get a feel for why the behavior of this patch of matter is the way it is. Okay, because right now you will just have to trust that the simulation is doing the job correctly. But if I want to get a physical understanding of why exactly this kind of structure is emerging, I need approximations. So we will also discuss some of these approximate techniques to derive nonlinear evolution. A couple of different things I will try to discuss. Okay. And then we'll see how it goes. So we have what? So we have today's lecture and tomorrow's lecture, right? So I will try to cover some of this today. and then tomorrow I will take a poll on what we would want to discuss. So let's go through this today. So as I said, the first thing to do before we even go into equations is to understand how length scales evolve in an expanding universe, right? And I already told you that there are two basic. So there is one very important length scale, which is the Hubble radius as a function of time, right? And the other important length scale to keep track of is the wavelength of whichever perturbation you're talking about. Okay, so remember, we will always now you have to learn how to think in Fourier space in order to understand linear evolution and cosmology. So when you want to think in Fourier space, you will say that let's always simplify your life, because although we are talking about perturbations in three spatial dimensions, so the density is the density of mass in three dimensions. So the density of mass here is different from the density of mass in that corner of the room. So I have a three-dimensional control variable which I have to keep adjusting, and I ask the question, what is the density here, there? This is quite difficult to track in our minds because we do not visualize things easily in three dimensions. In the sense, we can see things in three dimensions, but now if I tell you, visualize the temperature of this room in three dimensions, it takes a little bit of work. Instead, if I reduce the problem to one dimension, one spatial dimension, then I can plot things on a piece of paper or on the blackboard. So always work with simplified examples where you go away two of the dimensions in the problem and you think of only a one-dimensional system. And in this one-dimensional system, if I want to plot a density, I can easily plot it. I will say, okay, maybe it does something like that. All right, this is rho as a function of x at a given time. And we want to understand now, because we will start thinking in terms of linear theory, it will turn out to be very useful to work in Fourier space. So Fourier space is just the statement that here I can decompose this rho of x into a sum of sine functions, right? So here, for example, already visually the way I have plotted, you can see that maybe there is one sine function that looks like that. It's a large amplitude, long wavelength fluctuation. Then on top of that, there is probably a sine function that looks like this also. Because you see there are these short wavelength fluctuations, they don't have very large amplitude, correct? Compared to this overall big jump and dip and so on. These fluctuations I have shown here, they have a higher frequency, so they have a shorter wavelength, but their amplitude is not as big as the one that I have drawn here. Okay? So this is, by looking at curves like this, you can already try to visually infer what kind of wavelength modes exist in the Fourier spectrum of this rho of x. Right? So here what we are saying is that for this particular kind of rho of x, it seems like the long wavelength modes have high amplitude and the short wavelength modes have low amplitude. Okay, it will turn out, and then you have to ask in cosmology, is that what will happen, and and so on and so forth. So we will always now talk in terms of wavelength modes, right? So these are sine waves, and we will ask, given a sine wave, what is the amplitude of the sine wave? So I can control the amplitude of the sine wave. So I could have a situation which is opposite of this. For example, let me take something that looks like this. Okay. So now here what has happened is I have very high frequency oscillations. So very short wavelength modes, right? And their amplitude is quite high because at those short wavelengths I am jumping up and down. But the way I have drawn it, there is also probably a long wavelength feature like this. Okay. So now the situation is opposite. It's the long wavelength feature which has a lower amplitude, and the short wavelength feature which has a higher amplitude. Okay, so these kind of games one can play, and this is extremely simple to code, right? You open the Jupyter notebook, you code matplotlib, and you ask it to plot the sum of two sines, right? Sine of lambda 1 times x, sine of lambda 2 times x, and you add them up with an a1 in front of the sine lambda 1 and a2 in front of sine lambda 2. I have four numbers now, so you fix lambda 1 and lambda 2 to be something. Pick lambda 1 to be 10, lambda 2 to be 0.1. So lambda 1 equals 10 means it's a long wavelength. Lambda 2 equals 0.1, it's a short wavelength. I have A1 and A2, which are the amplitudes. Play with these amplitudes, right? Pick pairs of amplitudes, pick them to be equal to each other, see what it looks like. Then pick A1 to be 10 times A2 and see what it looks like. Pick A1 to be 1/10 of A2, see what it looks like. Okay, you should come up with answers. Good. So these are the wavelengths of, so now what we are interested in is to ask what is the wavelength of my perturbation. So we will call the wavelengths of perturbations as lambda. Lambda are not the amplitudes of perturbation. Okay, this is the number one mistake that all beginning cosmology students make. So that's why I spent like 10 minutes on this. We are going to talk about the wavelength of the perturbation. Amplitude of the perturbations is going to be decided by your theory. Right now, we are not talking about the theory of the perturbation. That's the dynamical theory which tells you how density evolves as a function of time. That will come later in the later slides. In this slide, we are only worried about the wavelength of the perturbation. Okay, so now wavelength of the perturbation, if I am talking about the proper wavelength of a perturbation, this is equal to some co-moving wavelength multiplied by the scale factor. Okay, so now what we will do here is to consider the proper wavelength of any perturbation or of any length in the universe, the proper length of some typical scale in the universe on the vertical axis versus the scale factor. So the scale factor in an expanding universe is a monotonically increasing function of time. It is a valid time variable as we discussed. So I'm going to place log of the length scale on the vertical axis and log of the scale factor on the horizontal axis. So the first thing to look at here is if I pick a wavelength here of perturbations and I say that I am going to choose a few different wavelengths with fixed co-moving wavelengths. Okay, a few different modes with fixed co-moving wavelengths, lambda 1, lambda 2, lambda 3. So imagine this is the co-moving wavelength. Okay, and I pick three such modes. I pick a long wavelength mode, lambda 1, then I pick a intermediate wavelength mode, lambda 2, and then I pick a short wavelength mode, which is oscillating very fast, which is lambda 3. These are my co-moving wavelengths. Good. If these co-moving wavelengths are fixed, how will the proper wavelengths evolve? They'll be proportional to what power of A? Will they be proportional to A squared? So I pick a co-moving wavelength. I say 1 megaparsec co-moving wavelength. How is the proper wavelength evolving as a function of time? Or as a function of A? How is it evolving as a function of A? What is the Friedman metric? The Robertson-Walker metric. ES squared is minus dt squared plus A squared of t dr squared plus stuff. So where is the co-moving length appearing here? Which term tells you about co-moving length? In this equation, where is the co-moving length appearing? Louder, I cannot. No, co-moving length. dr, right? So the dr squared piece is telling you about co-moving lengths. But ds squared is telling you about what? Co-moving length or proper length? If I fix my t, then it is talking about proper lengths, right? So what is the relationship therefore between a co-moving length and a proper length? Well, when I have a square, then there is an a square. But if I just talk about the length, there is just one power of a. Good. So a proper length is one power of a times the co-moving length. So now I am saying pick three co-moving lengths. Okay, 10 megaparsec, 1 megaparsec, 0.1 megaparsec. Okay, so the 10 megaparsec one I call lambda 1. 0.1 megaparsec is lambda 2, 0.1 is lambda 3. How do the corresponding proper wavelengths evolve? They'll be proportional to the scale factor. But now, so fine. So now take the proper wavelength corresponding to lambda 1. At current time, when a is equal to 1, lambda 1 is, we said, 10 megaparsec. Lambda 2 is 1 megaparsec. Lambda 3 is 0.1 megaparsec. What will happen at an earlier epoch? Let's say when a is 100 times smaller in the past. What will the proper wavelength corresponding to lambda 1 be equal to? Just do it quickly. So if I start with 10 megaparsec and I tell you that A is smaller than, correct. So it will be smaller by a factor of 100. What about the proper wavelength corresponding to lambda 2? It will be smaller than the proper wavelength corresponding to lambda 1 or equal to or larger? It will be smaller. By how much will it be smaller? The same 10 by 1 ratio that was there at A equal to 1. Okay. At any value of A, the ordering between lambda 1, lambda 2 and lambda 3 will maintain the same ratio as it has at A equal to 1. And that is simply because all of them are evolving proportional to A. So when I take ratios, A by A cancels out. Good. So that means when I do a log lambda versus log A calculation, now think of this, okay, notation is a bit unclear. This lambda is supposed to be the proper length, right? So when I do this log lambda versus log A, what do these curves look like? What should they look like? Straight lines with what slope? The lambda is proportional to A, so log lambda will be slope 1. Good. So log lambda versus log A, these curves, these dashed curves that you see are slope 1 curves. And there are 3 of them for my lambda 1, 2 and 3. And look at the ordering. Lambda 1 at A equal to, imagine this is A equal to 1 somewhere here. Okay. So at A equal to 1, lambda 1 is higher than lambda 2, lambda 2 is higher than lambda. And they are all slope 1 curves, so they maintain their difference. See, in a linear plot, the ratios would be the same. And the log plot, the differences between the curves will be the same. Correct? Because I took a log. So these are my straight lines corresponding to the 3 modes. Excellent. Now let's keep these modes here and we know how they are evolved. Now let's switch our focus to the other important wavelength, to the other important length scale in the picture, which is the Hubble radius. Hubble radius is C divided by H. This is the physical Hubble radius, proper Hubble radius. Okay, that's what we want to plot. We want to plot the log of a proper length. So we take log of the proper Hubble radius. Okay. Now, if you go back to your lectures which TP gave and maybe a little bit of what I also talked about, we know how the Hubble radius evolves in different epochs during the history of the universe. So you remember that if I have matter and radiation in the universe, then matter behaves like, density behaves like 1 over A cube, radiation density behaves like 1 over A to the 4. So matter density is diluting itself, but it is diluting itself slower than the radiation density. Matter density dilutes as 1 over A cube, radiation density is 1 over A to the 4. So as I go forwards in time, matter will eventually dominate over radiation. Okay, so at late times, I will be in a matter-dominated system. Let's assume that at late time there is no cosmological constant, because eventually maybe cosmological constant will dominate. But right now we just talk about matter and radiation. So now during matter domination at late times, how does the Hubble parameter behave? Okay, so it's not a very difficult calculation. You have to go to Friedmann equation. So Friedmann equation is what? H squared is equal to some proportionality constant times density. Right? H squared is like a density. And here you should have a sum of all the densities that you are talking about. But now we are saying that the sum of the densities is dominated by which density? Matter density. Okay. And matter density, so if this is dominated by matter density, then this scale is like what power of A? A plus A cube, A to the plus 3, A to the minus 3. A to the minus 3. So how does H behave? Minus 3 halves. So how does H inverse behave? A to the power plus 3 halves. Very good. So during matter domination, H inverse, which is the Hubble radius, C by H is the Hubble radius. C we don't care about because we are not worried about constants here. Okay, so this scale is like A to the 3 halves. So when I take log of this, what will I get? I'll get a 3 by 2 slope straight line. 3 by 2 is bigger than 1. So when I take the late time evolution, I should have a curve. So the red curve is supposed to be the curve corresponding to the Hubble radius. So at late times, the slope of this curve should be 3 by 2. Okay, and it is bigger than 1. So it should be a slope, it should be a line which is steeper than the blue curves. So that is what this is doing. It's a 3/2 slope. Okay. Now, suppose I have worked backwards in time. He said there is matter and radiation, and eventually matter is dominated. But that means in the past, radiation would have dominated. Because radiation goes like 1 over A4. So if I take A to smaller and smaller values, eventually 1 over A to the 4 becomes bigger than 1 over A. There will be a balancing point at which that transition happens. That is called matter radiation equality. Okay. So what we will do is we will simplify our life and say that from the late time epoch when matter is dominating up to the point of matter radiation equality, let me just draw a straight line. Okay, I'll not worry about the fact that there are actually 2 terms here. I'll just say up to matter radiation equality from forward, like from the future, there is only matter. And then at matter radiation equality, I will say that I'll suddenly jump to radiation domination. Although in practice, you should do a more careful job. You should take both of them, and then both of them will contribute. Okay. But let's say only one of them contributes. So then in radiation domination, let's do the same calculation quickly. Okay, so h squared in radiation domination is like rho radiation. This behaves like what? A to the power minus 4. So let's quickly say how much is h. H is like a squared. So h inverse is like a to the power minus, this is minus 2, and therefore this is a squared. Alright? So that means log of this quantity is a line of slope 2. 2 is bigger than even 3 halves. Okay, so 2 is bigger than 3 halves, 3 halves is bigger than 1. So 2 is definitely bigger than 1. So here there is an even steeper line. Okay, great. And now we'll work this backwards in time up to very, very early epochs. But now what happens at very, very early epochs? At very, very early epochs, we said that there must be a phase of inflation. Because without that phase of inflation, we cannot explain why the CMBs were uniform. During the phase of inflation, what does H behave? Okay, so now let's go back to our model of inflation. We said that in order to produce an inflation which is reasonable, we want the kinetic term of inflation to be much smaller than the potential term of inflation. And if you remember the energy density and pressure equations, it was telling us that rho and P should be such that P by rho is approximately minus 1. So inflation, the period of inflation basically behaves like a cosmological constant. Right? So now when there is a cosmological constant in the problem, what is h squared? So if h squared is dominated by a cosmological constant, then this is what power of A? Does it evolve? It has to be a constant. No, rho lambda is a cosmological constant, and we are saying that during inflation, the field which is doing the inflation basically behaves like a cosmological constant, slightly away from cosmological constant. So this is approximately e to the 0. Okay. So if h squared is a constant, then h inverse is also a constant. So I have plotted a constant. Okay. So now this leads to the following nice picture, because now you can ask this question. Now we have a plot in which we have the Hubble radius evolving as a function of time, and we have shown how physical wavelengths evolve as a function of time also. But look at what these wavelengths are doing. At extremely early epochs, take the longest wavelength, lambda 1. At extremely early epochs, the value of lambda 1, the proper value of lambda 1, is smaller than the Hubble radius. Okay, and then therefore the proper values of all of them are smaller than the Hubble radius, because lambda 1 is the largest. So all of these wavelengths are smaller than the Hubble radius at very early epochs, if there is an inflationary epoch. Okay? Only if this thing is constant will this happen, right? But now this is constant, so at these epochs they have gone below, and at this early epoch all of them are below. When perturbations have wavelengths that are much smaller than the Hubble radius, remember what we argued, that they are very, very small. So you can basically apply almost Newtonian-like arguments and say that densities close to each other will gravitate and they will grow. Okay, and in this case, what you will say is that there is a fluid which is relativistic maybe, and then it has some perturbations, and there will be sound waves that are supported by the fluid, and those sound waves will propagate, and the fluid will thermalize. So thermalization is allowed at these epochs, between these length scales, because causality is not violated by these length scales exchanging information from each other. But now, as time progresses, look what happens. As I go from this epoch to this epoch, right? Time is progressing towards the right. So as I go from left to right, at a particular epoch, the longest wavelength becomes larger than the Hubble radius. Okay? And now we said that our perturbation theory is going to tell us that when a wavelength of a perturbation is longer than the Hubble radius, basically due to causality, local causality, I do not have enough time for different parts of this sine wave to know about each other. So that sine wave cannot really evolve. Okay? Because otherwise causality would be. So when this happens, what we are expecting our equations to tell us is that during these epochs, when this particular wavelength is longer than the Hubble radius, the amplitude of the fluctuation corresponding to that wavelength will not grow. So whatever amplitude that fluctuation has at this epoch, when the wavelength became longer, it will freeze there and it will stay there. Okay. And then how long will it stay there? It will stay there until that wavelength becomes smaller than the Hubble radius again. Does that happen? Yes, it is happening. You see, I keep waiting, and then at this epoch, the Hubble radius becomes bigger and this wavelength becomes smaller. Okay, so now the wavelength has become smaller than the Hubble radius. So what one says in the jargon is that this mode has exited the Hubble radius and it has entered the Hubble radius again. Okay, so all of these modes are exiting the Hubble radius during the epoch of inflation, when h is constant, and they are entering the Hubble radius at different epochs. Okay, so this long wavelength that I have shown you here, it is entering during which epoch according to this plot? Matter domination. And the short wavelength that is shown here, it is entering during radiation domination. And I have tried to show you intermediate wavelength which is entering just around the time when matter and radiation are the same. Okay. So now this is going to lead to very interesting physics later, which we will see. And this is why I want to emphasize it here. Modes exit the Hubble radius during inflation. The long wavelength modes exit early. The short wavelength modes exit later, simply because of this picture. The modes which exited early will enter late. Okay, and the modes which exited late will enter early. So first out, last in. But because of this first out, last in feature, the shorter wavelength modes will tend to enter during radiation domination, and the longer wavelength modes will tend to enter during matter domination. So there will be some different physics that is happening when these modes enter the Hubble radius again, right? Because when these modes enter, the equations will say, okay, gravitate, now you're allowed. But what is the universe doing? The universe is radiation dominated. So it's like a very relativistic uniform path around. So the physical conditions are very different to those when this mode enters. Because now again, this mode will enter, equations will say gravitate. But now the universe is matter dominated. There is no radiation in it. Okay, and during matter domination and radiation domination, the physics will be very different. So there is going to be, we should expect just from not knowing any physics equations, nothing. You can just look at this plot and say there must be some very interesting differences between the behavior of long wavelength modes and the behavior of short wavelength modes. And now you ask the question, in this context, what is the comparison between long and short? Okay, how do I tell this is long? So long with respect to what? Now it is not with respect to Hubble radius, because Hubble radius is an evolving thing. We are comparing every wavelength at any given time with the Hubble radius. That's how we came to this picture. Now we are asking a question related to the ordering of the co-moving wavelengths. Those co-moving wavelengths are fixed numbers, always. So we are saying a particular fixed co-moving wavelength, is it a long co-moving wavelength or a short co-moving? With respect to what? Well, it's with respect to that wavelength whose mode enters the Hubble radius at the time of matter radiation equality. Because that is the thing which is causing physical differences. Okay, so you will see that the mode which enters during matter radiation equality, it has a special status. And then longer wavelength modes do something, shorter wavelength modes do something else. Okay, so this was a long discussion, but I hope it was clear. If there are questions, I will.
So are there modes which never leave?
Very good. So there will be modes which never leave the Hubble radius. So these are, and this is the idea of tuning the model of inflation so that you are always talking about observables today. Because modes that never leave the Hubble radius here, they should be such that you are not able to access them, at least in the CM. Because if you could, then you should see random fluctuations there or something. You should see something different happening there. Okay, so typically one adjusts the start and end of so the end of inflation is important. End of inflation should be such that your accessible modes are the observable.
If it's like the end is long enough, all modes must exist.
Yes, all the relevant modes must exit at some point so that they remain frozen, and then when they enter again, then they evolve accordingly. Yes. Okay, great. So let's proceed. So now we want to understand how the physics of these perturbations is going to be set up. So this I have already told you. So we can think of this as our initial condition. Okay, although this is not really the initial condition. Initial condition is inflation. But for the purposes of this lecture, I cannot give you the full history of perturbations before this point. So I will just tell you, think of this as the initial condition. This happens around 400,000 years. So at this epoch, if I calculate rho by rho bar for each of these components in the universe, remember I have baryonic density, I have radiation density, I have matter density. Radiation is described by a Planck spectrum whose temperature fluctuates from point to point. Okay, so when I talk about radiation, I really want to talk about the temperature fluctuations. But because that radiation is part of a relativistic fluid, I can also convert that temperature into an energy density using Stefan-Boltzmann law. And then I can talk about the fluctuations in that energy density. Okay? So the important part for this epoch is that the energy density of radiation and the energy density of the baryons are very close to each other, because the baryons and the photons are thermalized with each other, right? Just before this epoch, before hydrogen. So I don't have to think about the energy density fluctuations of radiation separately. They are whatever the baryon density fluctuations were. Okay, so for this argument. So those fluctuations are the temperature fluctuations that you see here, and we saw that they are of the order of 10 to the minus 5. So delta baryons or delta radiation is of the order of 10 to the minus 5. Dark matter at this epoch in the standard model will not be 10 to the minus 5 because it is not coupled to photons. Okay, it has never been coupled to photons if dark matter is truly dark. So dark matter has been evolving in the past of this epoch also. And what does it mean to evolve? Whenever I have large amount of density, that mass will accumulate even more mass. So I expect my densities to increase. We will see how these densities increase. But for the purpose of setting initial conditions, I will just tell you the answer here. The density contrast in dark matter is typically a factor 100 times larger than the density contrast in radiation and in baryons at this epoch. Okay, so but the point is that both of these are much smaller than 1. That is the purpose of writing these numbers. So you can safely assume that delta, magnitude of any delta in the problem is much less than 1. Okay, the CMB tells us this. If somebody asks you why you think that early universe has small fluctuations, we see that. That is the answer. It's an observational fact. Okay, so we use this and proceed. So now we said we want to bring in some equations to understand how these perturbations evolve. So the way to do this is to perturb the Friedman-Robertson-Walker metric. Okay, so look at this. I have taken the FLRW metric, in which I have rewritten things in terms of this conformal time. I can always change from any time coordinate to any other well-defined time coordinate. Okay, so all I did was to say that instead of this dt square, I will transform from t to tau such that dt is equal to a of tau to tau. Okay, and if I know a of t, then I can also just solve this equation. It's a differential equation between t and tau. I can solve this to calculate a as a function of tau, okay, or tau as a function of t or whatever. So I can do this, and then if I do this, then I get a term that looks like a squared t tau. Okay, and that would be the smooth and homogeneous isotropic metric. On top of that, I have added two functions, phi and psi. These are the perturbations in the metric that are allowed by general relativity. Okay, and we want to track these. And correspondingly, I also have to track perturbations in the matter. So for the purpose of this discussion, let's only focus on non-relativistic matter, forget about radiation and baryons. And now I have an energy momentum tensor, which earlier was rho and then 0, 0, 0. There was no pressure. But now my energy momentum tensor should also describe velocities, because my dark matter now is not part of a homogeneous and isotropic system. It has small inhomogeneities. So fluid elements of dark matter in local positions will have some motion relative to each other, which is not the same as the cosmic motion of of these fundamental observers who maintain a constant x. Okay, so I have some velocity perturbations as well, which I have to keep track of. So now my energy momentum tensor will be described by a density which has perturbations. So there's a 1 plus delta here. This rho bar is the mean density. And then the off-diagonal components will be related to the velocities. Okay, so not only the pressure will become different, but also the off-diagonal T0y components will become different. They will become proportional to the velocity. And the thing is non-linear actually, because I have delta and velocity multiplying each other. Here I have 1 power of delta. Here I have 1 power of delta with 1 power of velocity. Here I have 1 power of delta with 2 powers of velocity. Okay, so already the energy momentum tensor is non-linear in the fluctuation rate. And we want to set up a system in which delta, velocity, and the gravitational potential at the initial time are all small compared to 1. They are assumed to be comparable to each other. And we just denote them by an order epsilon quantity where we say epsilon is some small number. Epsilon is much less than. Okay, it's like a variable that we use to track the perturbations. So now you can turn the crank, you take this metric, you take this energy momentum tensor, you write down Einstein's equations again, right? If I did not have phi, psi, delta, and d, these Einstein equations would become what? If all these delta, b, phi, and psi are set equal to 0, what would the Einstein equations look like? What is the name that we give to them? What is this equation? Who is the first person after which this metric is named? Friedman. Alexander Friedman. So the equation that governs the evolution of H is called the Friedman equation. So now, instead of the Friedman equation, I will have some other equation. Okay, that other equation will involve phi, psi, delta, etc. Okay, and therefore, I will say that I already know the Friedman equation. So that equation, the new equation, will involve phi, psi, delta, b, and it will involve h squared also. So wherever I see h squared, I will just use the Friedman equation, right? Because I know h squared evolves like that. And then that will give me an equation for the evolution of phi, psi, delta. Okay, and I have to just play this game. So once I do that, I will get this kind of set of equations. So the first equation is kind of familiar because just look at the first term, forget the second two terms, and look at the right hand side. Okay, and these are higher order contributions. So these also for the time being you can forget because they have higher powers of psi appearing. So we said we'll linearize the system, so we only care about terms that are linear in all these variables. So what is this equation? Laplacian of psi equal to something proportional to rho bar delta. This equation have you seen? I've written it on the slide, but you must have seen it before. It's the Poisson equation. Okay, gravity is described by Poisson equation. And now what is happening here? There are a couple of extra terms. These are just saying that you are not doing Newtonian gravity. You are doing general relativity. So there are relativistic corrections to Poisson equation. Okay, and these corrections are written down. Good. So this is one equation that comes out of Einstein. Then you have to also do conservation of mass and momentum, right? Or mass, momentum, and energy. That is coming from the energy momentum tensor. So you go and ask what is the conservation of mass, conservation of momentum, conservation of energy. Turns out only the conservation of mass and momentum will be relevant here, and you will get this equation, right? So there's a derivative of the density contrast plus divergence of this delta times v equal to something. If this right hand side was 0, then this equation would be the usual continuity equation from fluid dynamics. Okay, and now there is a relativistic correction. And similarly, when I do conservation of momentum, I will get an equation that looks very much like Euler's equation. I have derivative of velocity plus v dot grad v equal to gradient of psi, right? And now there is an extra term here, but that is just telling you that the universe is expanding. So this expansion of the universe creates a drag kind of effect. Okay, so this is basically the Euler equation plus higher order. So now all I have to do is solve these equations. Okay, and they're not very difficult to solve because if I throw away the higher order corrections, I set them to 0. The remaining equations are linear equations, and I know how to solve linear equations. Okay, I have techniques that will help me solve. So this is a textbook problem now, and I can look up my mathematical methods books and I will solve the equations. So here is the result of solving such equations, and I have shown you the result for the gravitational potential as a function of time. Okay, this is taken from Dodelson's book. What has been shown here is the evolution of phi. Don't worry about these things, just non-dimensionalize the problem. Phi as a function of A for 3 different wavelengths of these modes. Okay, so now remember, what we are asking for is, given that we understand how the wavelengths behave, we want to know how the amplitude of those wave modes behave. So this phi is the amplitude of a particular wavelength. Right? That wave mode is labeled now not by lambda but by 2 pi by lambda, which we call k, the wave number. So for 3 different values of k, this is a small value of k, which means it's a long wave. Right? This is a large value of k, so it's a short wave. What did we say? Long values of long wavelengths, they exit the Hubble radius early and they enter late. So what is the way these curves are shown is that the curve is solid for the duration that mode is outside the Hubble radius. And after the mode comes inside the Hubble radius, the line style becomes dashed. So this curve entered the Hubble radius at this point. Up to this point, it was outside the Hubble radius. Okay. So, for example, at the matter radiation equality epoch, which is labeled by this vertical line, this mode was outside the Hubble radius. And it was evolving in this way. Basically, it was not evolving. This is what we expect. Right, that the evolution is very, very deep. And this mode basically remained a constant. And in fact, even after this mode entered the Hubble radius, as it turns out, it remains a constant. Okay, now this is a physical effect. The physics is telling, the equations are telling you that this is the solution. So this is what these long wavelength modes do. Look at the short wavelength. Short wavelength mode exited the Hubble radius late in inflation, and it entered early during radiation domination. So this mode is already dashed by the time you start seeing it. Okay, so it entered very, very early. And look at what has happened here. This mode, this is the gravitational potential. Okay, and this is the amplitude of the gravitational potential for a wavelength which is very small. What is it doing? It had some value in the initial conditions, then it entered the Hubble radius, and it immediately decayed. Its amplitude became very small. Then it came very close to 0, it oscillated for a while, and then it flattened. Okay? So what this is saying is that during radiation domination, the universe is so rapidly expanding that this gravitational potential cannot do much. Okay? It does not have any support. It does not have any mass around it which it can use to grow. How will gravitational potential grow at a particular point? It will grow if more and more mass enters that point, right? But the mass content of the universe is all relativistic. So this mass does not want to stay at one point. It is relativistic. It is moving with close to speed of light. So it is basically all the mass is trying to go away from itself, right? So this gravitational potential is not able to capture any mass and make itself do anything interesting. So this potential is decaying. And now as I wait for some time, or not as I wait for some time, as I look at modes that are longer wavelengths, I reach wavelengths which are entering later during radiation domination. So they are entering closer to matter domination. As I become closer and closer to matter domination, the effect of this rapid expansion decreases. My expansion rate slows down. And the dominant mass content of the universe is non-relativistic. So my intuition about gravity kicks in again. And now wherever I have an enhancement of density, I will tend to have more enhancement of density. So I will, and then the end result, according to the relativistic theory, is this. Eventually, I will have modes which enter deep in the matter domination, and their gravitational potential will basically remain the same. Okay, and you will see that these modes source density fluctuations with time. So what is happening here is basically a continuous transformation from short wavelengths where the mode has completely decayed to long wavelengths where the mode basically remained the same. So obviously in the middle, I will have modes which decay, but they don't decay all the way to 0. They will decay to some intermediate value and then they will stay. Alright? Good. So keep this in mind. We will come back to this in a bit. Okay. So now this is the same picture but shown not according to the gravitational potential but according to the density. So now I am looking at the density fluctuations and their amplitudes for different wavelengths. And now here you can see again I have these long wavelength modes and short wavelength modes. And in this case, the short wavelength modes they enter during radiation domination, but actually their growth here is not as rapid as the growth they will have later. Okay, so this is not very easy to see from this plot. That's why I don't like to show this plot first. It's much more clear when you think in terms of the gravitational potential, because there physically you can understand why the gravitational potential must decay during radiation domination. Then if you plug in all the equations and solve the relativistic Poisson equation, you will find an evolution of delta which behaves something like this for the short wavelength modes. For the long wavelength modes, the evolution of delta and the mode is outside the Hubble radius is basically no evolution. And then when the mode enters the Hubble radius, there is an evolution. Okay? And now at these very late epochs, what happens is that all of these modes of density are well inside the Hubble radius. You can see that in the previous slide also. At very late times, all the modes are inside the Hubble radius. And in this case, the equations actually simplify considerably, and the solution just becomes equal to what is written here. Okay? And what you can see here is that this evolution of delta, the k dependence is entirely captured by the k dependence of the potential fluctuations at the initial epoch. Okay, so whatever the potential fluctuation was doing as a function of k, the delta fluctuation inherits that. And the time dependence is all in one function of time. This function of time does not depend on k. Okay, so the modes they all behave in the same way. They grow together at very late epochs. So this is a hallmark of this linear system of equations, and the evolution of this function of time is governed by this differential equation. It is again not very difficult to solve. You can put it on a computer; it's very straightforward. Or you can say that during matter domination, I want analytical answers everywhere. So let's look at matter domination. I plug in the values of H from here for matter domination, and it turns out that the equation simplifies to this, and then you'll find that delta proportional to A is actually a solution. So at late times, all the density contrasts grow like A at any given. Okay. So this is how the density perturbations behave. And now let's go back to this this picture, because it is again useful to understand what is happening to the strength of fluctuations. So here what we are saying is that let's consider A equal to 1. So at A equal to 1, what are the amplitudes of different wavelengths? The amplitude of these, long wavelengths is some high value, and the amplitude as I go to smaller wavelengths, the amplitude decreases, and it decreases quite a lot, because here by the time you reach this K2 MPC inverse, the amplitude has basically gone to 0. Okay, and in between there is a place where the amplitude is some intermediate level. So now from here, what I want to do is to calculate this quantity, which is the 2-point correlation function of the delta fluctuation. We studied this for a Gaussian random field yesterday. And now I want to do this. This P of k is called the power spectrum of these correlation. It is basically the variance of the fluctuations at that value of k. We discussed why this is only a function of mod k and dot of k. Okay, so I want to know what is the form of this P of k according to my theory. So it turns out that when I do this, this P of k will be related to these fluctuations. So these you can think of as the primordial fluctuations modified by whatever happened during the matter to radiation to matter transition, and then this relative ordering of these amplitude of fluctuations is inherited by the fluctuations in delta. Okay, so I convert all of this into a power spectrum, and what I see is something that looks like this. So I have an initial rise in power and then a fall at large values of k. So this is P as a function of k. What is this telling us? At small values of k, these are very long wavelengths. Here, I am talking about things which have not evolved very much. So the shape of the power spectrum here has to be told to me by the theory of inflation. And we already saw what the theory of inflation tells us. For the curvature perturbation, it makes a prediction, k to the power ns minus 1. Right? When I apply the Poisson equation, characteristic Poisson equation, etc., and I take that curvature perturbation into delta, this thing becomes P proportional to k to the power ns. Okay, this comes from inflation. So P proportional to k to the power 1 ns. This comes from inflation. And that ns, as I told you from observations, is something like 0.97. It's different from 1 by a small amount. So this quantity here is basically something that is proportional to k. And this is coming from the primordial theory that generated perturbations in the first. At the opposite side, at very large k, we are talking about those modes whose potential decayed very, very much because the universe was radiation dominated and the densities could not grow very rapidly. So the power here you can see is very small. And as you go to smaller and smaller wavelengths, larger and larger k, the power becomes even smaller. Okay? So I have one regime here where I have low power, one regime here where I have low power, and in between there is a regime where I have a peak of power. This peak occurs at the wavelength which entered during matter radiation equality. This is a very interesting feature which can be looked for in observations. So if I somehow have a means of measuring this power spectrum in data, I can go and ask the question, does the power spectrum have a peak or not? Okay. Because if I can find the peak of the power spectrum, then the location of that peak gives me the value of the co-moving wavelength which exited during matter radiation equality, for which I have an analytical answer from my theory, and that depends on these parameters, omega matter, omega radiation, etc. So it gives me a way of measuring these parameters if I can locate the peak. Okay. So now one interesting thing that happened in the 1980s was that people didn't know about the cosmological constant. They didn't expect something like the cosmological constant to be there. So they were always thinking in terms of what is called this SCDM model, standard CDM, in which omega matter is basically 1, omega radiation is 10 to the minus 5, and omega curvature is 0. Okay? So this is the prediction for the power spectrum in that model. And data was starting to probe these scales here. So if this model was accurate, then you should have seen a peak of the power at these scales. But you did not see a peak of power at those scales. So this was in 1989, 1990, which is at least like 4 or 5 years before the supernova team came and did its cosmographics. Okay, so this was large scale structure, which was producing these results. We did not see a peak of power in the observed galaxy power spectrum. Inference was that a matter-dominated universe alone cannot explain large-scale structure data. And in fact, there is a paper from 1991 which shows that if I introduce a cosmological constant in the problem, then the peak of this power shifts to smaller values of k. Okay, simply because when I have a cosmological constant, the value of omega matter has to decrease because I want a flat universe. So omega matter plus omega lambda should be approximately 1. And omega radiation is 10 to the minus 5 because CMB we know. So now if omega matter plus omega lambda is 1, then omega matter cannot be 1. Omega matter will be smaller. Cluster cosmology was already telling us that omega matter cannot be 1. It has to be smaller. So these people said, let's believe the results of cluster cosmology and allow for an omega lambda. Lo and behold, because omega matter became 1 now, because you allowed for an omega lambda, the peak of the power shifted to lower k, and it became consistent with the data of large-scale structure. So large-scale structure plus clusters was telling you in 1990 already that probably there needs to be an omega lambda. Okay. This is a very interesting historical note to keep in mind when you think about the fact that the Nobel Prize for the accelerating universe was given to the supernova, and there was no mention of the large-scale structure. Okay, so it's interesting history. Good. So I will wrap up with linear theory only now because I don't think there is any point in discussing nonlinearities at this stage. We can discuss nonlinearities tomorrow. So let me spend 5 minutes and then I will. So this is a different way of representing the same linear theory power spectrum. So this is called the linear theory prediction for the power spectrum. Right? It makes sense. Power spectrum is this 2-point correlation function in k-space. Linear theory, which we have been discussing, makes a prediction for this. So it's linear theory plus inflation. So inflation predicts this part, Linear theory predicts the rest. And depending on whether you put in a omega lambda or not, my prediction will change. Okay, so this is the idea. This is another way of showing the same thing. Where remember I said that the power spectrum, if you do dimensional analysis, will have units of length cube. So I can make a non-dimensional quantity out of it by multiplying by k cube. So in the literature, it is conventional to define this k cube e divided by 2 pi squared. This is the dimensionless power per logarithmic interval in k. Okay, so this is the way it is defined. And I can plot this quantity, it's dimensionless now, so I don't have to worry about units. And I plot it as a function of k again. In this case, the part which is k to the power ns becomes k to the power 3 plus ns, so k to the power 4. Okay, so there is this again steep rise here, k to the power 4 roughly. And then this part, which is falling here, it gets enhanced by a k cube. Okay, so now you have to ask what happens to this. So the theory, linear theory in this regime actually predicts an analytical answer for this. It says that this power here should be proportional to 1 over k to the power 3 times log of k the whole square. Okay, so the linear theory prediction for large k much bigger than k equality, is log of k the whole square divided by k to the power 3. Okay, so what that means, okay, this 3 really depends on ns, this is approximately. So what happens here is that when I take k cube multiplied by this, the k to the power 3 gets cancelled out. Okay, so this is an analytical answer now, and there is a very slow increase here, the log of k the whole square. Okay, so this is the nature of the power spectrum in a universe which is dominated by cold dark matter. So cold just means that there is no initial velocity dispersion. So you can, this is in fact the reason why in the linear theory equations, I didn't talk about energy conservation. I just said, let's talk about gravity, which is the relativistic Poisson equation. Then there was the continuity equation, which is mass conservation. Euler equation is momentum conservation. And we stopped there. Okay, and the reason we stopped there is because we are assuming a model of dark matter which does not have a temperature. So I don't have to worry about its energy conservation. Its internal energy is set to 0 and it takes care of itself. Okay, so in such a universe, the power spectrum of such matter fluctuations will just keep increasing. It will keep increasing. At smaller and smaller length scales, I have more and more power. So imagine what that is doing here, right? So the universe is not like this. It is more like this. Because I am saying that at long wavelengths, my amplitudes are smaller. Long wavelength means small values of k. So I have a smaller amplitude. As I increase my value of k, I go to short wavelengths. And my short wavelengths, my amplitude of fluctuations increases. So I have a system which looks more like this than like this. This is the prediction of linear theory, right? And now people are also worried about what happens to arbitrarily large values of k. Okay, does this keep increasing or not? And now you enter a regime where you have to ask a particle physics question. What is dark matter? So is it correct to say that there are no temperature fluctuations of dark matter? There is no temperature in dark matter. It's perfectly cold. There is no valid physical model that we can think of where this is actually realized. That I have a perfectly cold system. All models of dark matter will produce a fluid which has some temperature at least at early times. Okay, so in such a situation, what will typically happen is that this increase will not go on forever. There will be a scale where beyond that scale, I will have zero power. So I will turn around in this amplitude power spectrum and I will go to 0. So at these small scales, I will not have any power. Okay, and then people give names to these models. So these are, for example, bomb dark matter particle models, where the mass of the dark matter particle corresponds to 1 keV or 10 keV, etc. And in the standard models that one is used to thinking about, cold dark matter, there the particle mass is more like 100 GeV. So that 100 GeV will have a turnaround also, but that turnaround will happen very, very late. Okay, so here you can see on top, instead of a inverse length, they have converted it into a mass scale by saying how much mass will be enclosed in that length in a mean density universe. Okay, so now what you can see is that as I go to larger k, smaller lengths, I get less mass. So here I have 10 to the minus 6 solar masses, which is like Earth mass scales. So 100 GeV wind would actually have a turnaround which is just beyond the scale that has been shown. Okay, so these are the kind of models that people think about. And the reason that these are interesting is because today we don't have any particle physics candidate for dark matter which everybody agrees on. LHC has not discovered anything interesting, right? So we do not have any experimental verification of a particle which can reliably be called the dark matter in the universe. So it is cosmology again which has to come up with ways of differentiating between different particle physics models. Okay, and how would you do this? So the power spectrum of matter fluctuations is in principle observable in the universe. You could look for probes which will give you, whose clustering strength will give you a measurement of what this power spectrum should be. So if you can come up with probes which allow you to measure the power spectrum at these scales, at k of 10 or 100, right? Then the data should be able to tell you whether your power is here or here. Okay. So from the data, you should be able to say, is my model with a 1 keV dark matter particle consistent with the observations or not? So this is the game people are playing now. For example, the Lyman alpha forest has fluctuations, and these fluctuations can be measured, and their power spectrum can be calculated. And this is a big industry now. The Lyman alpha forest power spectrum has been measured in the Sloan Digital Sky Survey and its successors, the BOSS survey. And these are placing very tight constraints on the mass of the dark matter particle. Because what has been seen is basically that the power spectrum looks essentially like the solid line. Okay. And this turnaround has not been seen. So if the turnaround is not seen, what can I say? So look at this, right? A 1 keV particle will produce a turnaround at this value. A 10 keV particle will produce a turnaround at this value. A 100 GeV wind will produce a turnaround here. So if I go and measure the power spectrum in this region, and I see that it looks like the solid line, the data now look like the solid line, I can say that a model which looks like the 10 keV or the 3 keV particle is not consistent with the data. So if at all there is a particle with a mass which is, some finite value, that finite value has to be at least larger than 3 or 10 keV, right? Depending on where the data is. So of course data will have noise and so on. So then you have to do a proper statistical analysis, and then with some confidence you will say that the dark matter particle mass is larger than some value. So the current limits at 95% confidence are something like 5 keV. Okay, and these are very interesting from the particle physics perspective because they rule out a large class of particle physics models because the data are telling us. And these are cosmological observations. These are not experiments that you're doing in the lab. Okay? So this is, I think, where I want to stop for today. Okay, so we will discuss nonlinearity. Any questions about this?
For the dimensionalities of data, isn't the numerator a linear density and the denominator volume?
Here? No, this is rho bar, so it's a volume average density. So both are densities, so this is dimension. So rho bar is the mean density of the universe, and rho is the actual density at that location in space. So at any given location in space, I don't have the mean density. Right? My density can be higher or lower. I'm just asking how much higher or lower, by what factor.
Since we are taking only one dimension, doesn't it depend on mean? How should we depend at what point? How can we
You can always take a tiny volume around. Density is a locally defined quantity. So I can take an infinitesimal volume element compared to the volumes that I care about. If you want to know in practice how you do it, then in the simulation box I showed you a density. You can ask how did that come about. You basically put a grid, and then at the resolution of the grid, I produce that density. Right? So I put a little cube, and I count all the mass in that cube, and I take the mass divided by the volume of the cube, and I call it the density at the location of the center of the cube. And then I go only to the next cube. So I don't resolve the density between the centers of two cubic elements. Okay, if I want to resolve that density, I have to make a smaller. and then n is 1. So what I showed you is at a particular choice of resolution, and at a different choice of resolution, you get a slightly different result. You will get more power, you get more noisy looking.
If at all the density of a point, the wavelength that exactly enters at the matter, will that never change or fluctuate in the linear?
No, it is linear only. It does fluctuate. So the amplitude of that fluctuation is also there. In this plot, you can clearly see there is in fact, that amplitude is the strongest amplitude in this dimension full P of K. This P of K has a peak, no? And the location of the peak is a value of K. That value of K is the wave number which entered during radiation matter equality. What is the question?
Before the density was in the matter radiation, in the matter dominant, the density was somehow constant.
This is not density, this is gravitational potential. This is gravitational potential. This is the plot you were talking about. This is gravitational potential. Gravitational potential is related to density through the Poisson equation. So it's easier to think at late times, because at late times the Poisson equation is the usual Poisson equation. Okay, the relativistic corrections disappear, and the usual Poisson equation is Laplacian of phi behaves like density. Okay, I'm forgetting about the dimension. But these are the fluctuating pieces. So if I do Fourier transform of this, I will get k squared phi minus k squared phi k. This will be like delta. Okay, so there is a relative k squared between them. So phi k becomes so you are worried that this phi k is becoming a constant. Good, yes, but then there is also a time dependence, right? So there is a rho bar and a k actually in the full Poisson equation. So it's not just the k dependence is determined like this, but then there will be a rho bar times a also. Okay. So the rho bar times a, I think I've messed up something. I think this should be a squared. Okay, it's a rho bar a squared. So this thing is like delta divided by a. Okay, so that's why when phi becomes constant, delta is proportional to a. Delta grows. Phi remains the same, delta increases. That's the idea. Good that we clarified this. I hope everybody else also follows. He was asking, there's a confusion that phi becomes a constant, but then I was saying later that this delta is increasing with time. It's increasing proportional to a. So where did that come from? It's very easy once you remember what the Poisson equation tells you. Poisson equation says that Laplacian phi is like rho. And there is a squared because this is a co-moving Laplacian. Okay, so Poisson equation says that physical Laplacian is equal to rho. So now rho is really the fluctuating rho. So it is actually delta rho. Okay, rho minus rho bar. So that thing, when I adjust, I will get an a squared extra here because of co-moving to proper, and I will have a rho bar here, and then I'll have delta. Delta is the fluctuating quantity. So now if I go to Fourier space, I will have a k squared phi k because Laplacian becomes k squared in Fourier space. Right hand side I will have a delta k, and then this time dependence will be rho bar a squared. Rho bar is matter density, so it is 1 over a cube. So this becomes 1 over a. So now if I look at the ordering of k's, it will be whatever it was. But phi amplitude became constant for all the k's, right? So delta becomes proportional to a for all the k's. That is what is happening. That would be. Okay. All right. So if there's nothing else, we can stop. There is something on the chat. Whatever I said, I want to see basically there's an equation which picks up a solution is the Bessel. Okay, so far away the Bessel functions, and the Bessel function is Bessel 1 here, so there is a 1 over k to the sum power. So it oscillates and
This is not diffusion.